I'm a cool guy. Anyway, so I'll be teaching category theory. Alright. So,
I'll be learning category theory.
yeah. So I'm teaching category theory. And Essentials of Math is doing the
Projective geometry.
Yeah. As it relates to competition math.
Yeah, category theory is just a bunch of arrows.
Yep, that's what category theory is. That is in fact. Alright. Isn't it just a bunch of arrows? Yeah. Could you show us how to tell if two knots are equivalent? Like, show us... It's not... I'm sorry, guys. It's not Ask Me Math. I messed up on the thumbnail, alright? Let me change it. Change thumbnail.
It's changed for me, so...
Let me just find an epic, just random screenshot I have on my computer. Yeah, alright. So, does the blue show up well on stream?
That's pretty good.
Okay, what about the green? Ooh. Is that better?
Oh, I can't see yet. Hold on. Yeah. Well, I say the blue is better, but
yeah.
I mean it's more vibrant. It's easier to see.
Alright, we'll just go with the blue. It'll run out pretty quickly, so I'll have to get a new marker. So, Essentials of Math. What is, in fact, your real name?
My real name is Andre.
That's crazy. I don't care.
That's very... Oh, okay.
Alright. General relativity. It's not... I'm sorry, guys. It's not Ask Me Math. I'm not answering your math questions. Alright, we'll get started with the definition of a category. Even though, Essentials of Math, you are a very smart man, and you already know what it is. Is that not correct?
Yeah, I know the definition.
Yeah, but we're gonna start with it anyway. So the idea of category is, as you know, this very smart man, Essentials of Math, is to generalize the idea of functions and sets, or structure-preserving maps, and whatever structure. Okay, what happened? Can you help me pick the best credit card reward program? Oh yeah, I know all about credit cards. Alright. So the formal definition is you have two collections, and they don't necessarily have to be sets. So they're just collections, just random collections of objects. Or just things, because there's actually two types of structures. There's one,
the
objects,
meta category.
A, B, C, D.
Oh.
That's what it's called in McLean. No one says that anymore.
Yeah.
They just call it a general category. So these,
okay.
I'll write as an element of the object of the category. And the category I'll write as like a fancy letter. Usually C, D, E, you know. Alright. Number two is we have arrows. Given letters like F, G, and H. And those are going to be called, arrows of the category. And they're going to be written as elements of R, C. A-R-R-C. Alright? Three is that for each of these arrows, so for every arrow F, you know the upside down A symbol, right? Okay.
Yes.
Yeah, okay, good.
I have indeed taken an actual math class.
That is crazy. I can't believe that. Alright. It's just sometimes people don't know and they're confused. And so I have to make sure. Alright. For every single arrow, there's two objects. The domain of the arrow, which is an element of the objects, and the codomain of the arrow, which is also an element of the objects. Alright. And we'll usually write it as F. A colon is from the domain of F into the codomain of F, or F is from A to B. Alright. Number 4 is that we have a composition, which takes in, so if we have an arrow, F, which is from A to B, and we have another arrow, G, which is from B to C, you can create a new arrow, G composed F, which is from A to C. You've probably seen something like that before, like all over the place, everywhere, literally everywhere.
Never.
Yeah, I don't think anyone knows about that. All right.
Forbidden math.
Number 5 is for every object A of the category, you can create a morphism, or an arrow, or you can also call it a morphism, which is from that object to itself, and it has the property that any arrow, G, which goes from A into another element, has it that G composed 1A is equal to G, and that any arrow G, which is from some other element into A, you have it that 1A composed G is G. Same idea, just it's a two-sided inverse.
Identity.
Right. Identity element, yeah. Not inverse, sorry, yeah, no, identity. The arrows probably don't have inverses unless they're isomorphisms. Alright. Is that it? I don't have notes. I should get notes.
Then there's, that's like the general category.
I don't think there's anything else.
Then there's associativity and
yeah, those stupid basic stuff. I want to make sure I'm getting all of them though.
what's the other thing?
The introduction. Associativity, identity. That's it. Yeah, that's it. Composition, identity, and associativity. Yep, we're good. Okay, and 6 is that F composed G composed H is F composed G composed H. And other than that, I think we're good on that definition. Alright, so an example of a category is the category of sets. It's usually just called set. Alright? So the first thing we need to do is specify the objects and then specify the arrows between those objects. It's pretty obvious. The objects are going to be sets, and then the arrows are going to be functions. Functions F between two different sets. Alright, do you know any other examples of categories in your own exploration?
A category of topological spaces.
That is, in fact, a category, yep. So, category of topological spaces, you have topological spaces, X with the topology, and then the arrows are going to be uh, continuous functions f between two topological spaces. And I should also specify the composition on this one. Composition is obviously going to be function composition. Alright, and then here, the composition is also function composition. Yeah, they're just talking about stuff not related to what's going up on here. So I should stop looking at the chat. Alright. Do you know any other examples of categories?
The category of groups?
Yeah. So you can either
category
call it
of categories.
That is coming up, yeah. You need to know about a little bit more. So I'm starting at a base knowledge, so there's no holes. So you can either call it GRP, or just group written out. So obviously the objects are groups. The arrows are homomorphisms.
Oh, so one question about
yeah.
For the topological space category, for the arrows, they don't have to be the same topology on the sets, right? Those are different topologies?
Yeah, those are different topologies, sorry.
Okay, good.
Yeah, I need to write a prime there. Yeah, you can't have the same topology on different sets. That would make no sense.
Yeah.
Composition is obviously function composition. Alright, so I think the introduction to it is really easy. You don't need to know that much about math. But once you get into it, it's really cool. And it goes really far into a lot of math topics. Let me go ahead and follow some more about the book. Alright?
Jesus.
What's happening?
Your channel is useless.
Why are you shooting at all? Just talk with your friend. Your channel is useless. You're not even a mediocre explainer. Oh my god, that's so mean. Alright, if you don't want to watch it, you don't have to watch it. So the thing is that the person I am talking to is, he already knows about category theory. If you want to learn category theory for yourself, watch my series on category theory. I think it's one of the first that comes up if you just YouTube search category. I understand, so your statement is false. Dang.
Message retracted. Oof.
Ooh.
Alright. That's also an understatement that I already know category theory. I just know the definition of a category.
Yeah, okay. I'm going to introduce something you probably already know about. Functors.
I
Do you
don't
know about
them too
functors? Hey! Look at that. Alright. So a functor is like a morphism between two categories.
Yeah.
C and D. There we go. Gotta fix my fancy script. Alright. And it has two different operations. One is acting on the objects. So it's what's called an object function, even though it's not really a function because it's not necessarily sets. But it acts on objects of the category. So for every object A of the category, there exists a unique object F of A. And I say unique, but really it's just F of A, which is an object of D. And I know I didn't write OB there. So for every object, there is an object in the domain. There is an object in the codomain. For every arrow in the domain, there is an arrow f of f in the codomain. So it's like a function that acts both on the objects of a category and on the arrows of a category. Alright? And the other requirement is that for any pair of arrows that are, so we have a string of arrows like this, and this is all in C. There is, you have the rule that f of G composed F is equal to f of G composed f of F. And note that this is the composition on C, and this is the composition on D.
On D.
Yeah. Please, I need your email. My email is fematica@gmail.com. FEMA.
It's in the description.
TIKA. Is it? I don't know if it is on the live stream.
I think so.
I think just my Patreon is. Yeah, just my Patreon. Or chill.
Oh, it was on the other one.
Yeah, because the other one didn't suck that I made in 5 minutes. I spent time making it because I thought I could start the stream, but I couldn't start the stream. So all right. Okay, so that's the idea of a functor. An example of a functor is actually pretty hard because I can't think of one right now. A common example of a functor is what's known as the forgetful functor. So, sometimes you'll call it U. So there is a forgetful functor from the category of groups down to the category of sets.
Yeah.
And what it'd do is it just
forgets the multiplication.
And it just forgets the multiplication. Yep. And then if you take a morphism phi, that kind of looks like a phi there. It's a U. Then you just get the same morphism phi, except now it's on the sets. So you might put a little tilde over it or something. I don't know. So it just forgets that there are operations on the group. Alright, you can also do this with topological spaces where it forgets that there's a topology on the set. And so on and so forth. Another good example of a functor is the power set functor. The power set functor takes in a set and it outputs another set. So it'll send a set X to the power set of X. Alright, the set of all subsets. Alright, and it'll send a function between X and Y to the power set of that function, which is from the power set of X into the power set of Y. And how you define it is that it'll send a set of subsets A to the image of that subset under a map F. So it's just the image of that subspace. So you could write it like that as well. Alright, so why is this a functor? Well, if I did power set of G composed F. So this is now a function on sets. So I can on the power sets. So I can apply this to a subspace A. From the definition, this is equal to G composed F applied to A. So the image of A along G composed F. Which is also equal to, by the definition of composition, the image via G of the image via F of that subspace A. which is then really the power set of G applied to f of A, right? From the definition. Which is then the power set of G composed the power set of f applied to A. So that's a proof that it is a functor. Does that make sense?
Yep.
All right. Oh, I'm an idiot. I forgot a very important part of the functor definition. Is that it sends identities on an element
To identities.
to the identity at its image. Sorry, that's actually important. I forgot about that. Sorry. Open problem garden. Help me, please. Integral cosine of it. What's up with the integral? This isn't Ask Me Math. Is the thumbnail changed? Alright. So, now let's also prove that part of it. So, the power set on the identity function on a set. Alright, we have to apply this to A, which is going to be the identity function on X applied to that subset A. And because it's the identity function, it's just A, which is also the identity on the power of X applied to A. Does that make sense? Are you there? Yeah, okay. So, let me go ahead and explain this. So, the identity function on a set sends an element X to itself.
Yeah.
Right? Alright, so the identity on the power set of X, what you need to figure out is it needs to be from the power set of X into the power set of X. It'll send a subset of itself, of a subset of X to itself, right?
Uh-huh.
So this functor power set of X, or power set, can take in this function, which is the identity, from the definition right here. When I apply this onto a subset A, I just do the image along that function. From the definition of what an image is, you do the object applied to A for every A in the subset.
Mm-hmm.
It's just applying it to every single element. From the definition of the identity, you just get A. It's for A, an element of A, which is just A.
And that's just
which
A.
Then, by the other definition, is the identity on the power set applied to A. Yeah. Alright, so those are the two things you need to do in order to prove a functor. You have an object function, you have an arrow function, proved it preserves composition, and that it preserves identities. Is the audio out of sync with the video? Yeah, I don't know. I can't help it. It's OBS and my Mac laptop. Alright, so the thing about functors is that you can compose them. And you're not going to believe how you compose them. It's going to be crazy, trust me. So if you have three categories, C, D, and I don't know how to write a fancy E. Why did I do this to myself? E. And you have functor F between those two and G between those two. You can define a composition, which you usually just write the two functors next to each other.
Yeah.
When applied to an object A, it's just going to be G of F of A. applied to an arrow f is just going to be g of f of the arrow. So let's go ahead and prove that this is a functor. So I'll go ahead and prove the identity one first. So the identity on an object A, when I do this, this is g of f of 1 on A, from the definition of how it applies to arrows. Which then, by the fact that f is a functor, you can then do 1 at f of A. So when you apply the functor, it preserves the identity. You can move it down there. And then, because g is also a functor, you get 1 at g of f of A. So then, this is also equal to, by the definition of how it applies to an object, gf of A, which is exactly what you needed to do.
Yep.
Alright, and then for composition, it's a really easy proof. I think you can do it on your own. I don't need to explain it. I think this gives you the lowdown. Alright.
Proof is left as an exercise for the reader.
Alrighty. Okay, what should I do next? I know what I should do next. There is an identity functor, which I will write as ID on a category. So it is from a category to itself. You can probably guess it sends an object to itself and a arrow to itself. So that is an identity functor. So I think you could probably tell where this is going. We have composition, we have arrows, we have objects, and we have an identity.
Category of categories.
Category of categories. So we call it cat. So the objects are going to be categories. The arrows are going to be functors. And the composition is the composition of functors. Alright. So now, a weird thing is that the category of categories is an object of the category of categories, which is a whole other thing about the recursion in category theory. And which is sort of why I love category theory, is that you can just keep building up structures on top of each other, and it's all, like, they all relate to each other. It's really cool. Alright, now I'm going to give you some more advanced examples of functors, just so you get a better idea. The first one is the fundamental group. You know what the fundamental group is, right?
Yeah.
Yeah. So it will take you from the
category, topological spaces.
However, it's under homotopic equivalence. So if you don't know what homotopic equivalence is, maybe you should watch my video. Just saying. Alright, so this is the equivalence classes of functions between spaces, where if two maps are homotopy equivalent, then that means that they're both in the same class. So this just makes it so that homotopic maps are viewed as the same object, which makes it easier to define this, actually. Actually, maybe I should just do... Alright, I'll get rid of the homotopy equivalence right now, just because I'm scared. I'll put a little star down here. What the star means is that you'll have a topological space as an object, but it'll also come with a point on the topological space. So these are the objects, and then the morphisms between them, P prime, are just continuous maps that preserve the point, I think. Wait, let me make sure. Top star. Spaces with selected base point preserving maps. Yes. Alright. So it's continuous maps that preserve the base point that it's also given. So that little star means pointed topological spaces.
Mm-hmm.
Alright? So the fundamental group will take in a topological space along with the points, and it will output a group, which is, not necessarily abelian, so the best we can do is just group. And so the statement that this is actually a functor is actually stronger than just it assigning topological spaces to groups, because what it also tells you is that for every map, you can induce another map F, which is between the two fundamental groups. So for every continuous map F that preserves the base point, you can create a new map, which I think if I put the if I put the little star in the wrong spot, I don't think it matters. So you usually write F star for that instead of pi 1 of whatever. You're pretty active in the chat, aren't you? You can try to
They're telling you to fix the lag by unplugging and replugging your mic.
Me.
Alright, I can hear you now.
Okay, you can? Okay, good.
Yeah.
Yep, okay, it's working now. If that didn't fix the lag, I don't know what will. A 500 integrals video? Oh my god, I can't beat that. There's no way. I was planning on beating the record, but I think 500 integrals is a little much for me. Alright, does this example make sense?
Sure.
Did you get it?
We'll pretend that I did.
Alright, the fundamental group takes in a topological space along with a point, outputs a group. And then for every continuous map, there's a map between the fundamental groups. That's all you really need to know. Alright?
Yeah.
So don't worry about the specifics yet. So another example is homology, which you're going to learn about. And it takes you from topological spaces under homotopy, and then it will output a group. So this is even a little more general because you don't need the... I think it could be an abelian group. Yes. AB. I don't know why I got confused on that. Of course it's an abelian group. Alright. So this is sort of a better concept, and it can be for any integer, positive integer n, non-negative integer n, and takes in topological spaces under homotopy equivalence into abelian groups. So that's also a functor. So functors are seen everywhere in every field, especially algebraic topology. That's where the idea actually came from initially. It was Ehlenberg, and he was like, yo, what if we just had functors, yo? And then, yeah, he made functors, then he made category theory. It's crazy.
Nice.
All right. I'm going to talk about, we're going to take a step back from all of this crazy functor stuff and talk about more examples of categories.
Oh God.
All right.
When
so
do
the
the
functors,
examples stop?
the examples never stop until you're dead. All right. So a good example is 0. So the objects are it doesn't have objects, and the arrows is that it doesn't have arrows, and the composition doesn't need to be defined because there's nothing there.
That's
Yep.
the best category.
I know, it's my favorite. The category 1, which basically can be summed up by this thing. Just that's the category. You have a single object, a single
Nice.
arrow, and that arrow is the identity. Another
That's
category
the trivial
is
group.
2. Yeah, that is the trivial group. All right, so you have 2 objects now. You have the identity on each. And get this, you have an arrow between them. It's crazy. I know. It's getting a little wild here. All right, then we also have the 3 category. You have 3 objects in a big triangle, and you just draw 3 little arrows. Then you have all the identity arrows. All right, the composition, which you actually have to define now, is that this one, if I call it F, and I call that one G, so G composed F, and I call that one H, is H. So these 2 compose to give that one. And then, of course, the other ones are identities. Mm-hmm. All right. Then there's one more, just really easy category to go over. And it is the double arrow category. You have 2 objects, and you have 2 arrows between them. Like that. All right. The next example is going to be preorders. Do you know what a preorder is?
Nope.
Yeah. All right. So it's basically like an order. So you need to have a less than or equal to operation on P prime. Alright, so you have a less than or equal to operation, except you don't need to be able to compare any 2 of the elements. So it could be something like this. So this is the lowest level of elements, this is the medium level of elements, and this is the largest level of elements. You could have something like this. So this one is lower than that one in this chain. This one is also lower than that one. These 2 are both lower than this one, except you can't compare these 2. There's nothing defined between them. Alright?
Okay.
And these arrows I actually drew give you what the category actually is. So, and you do need to
Well, they would have to be identities, right?
No, wait, I'll show you. This is why it's less than or equal to. So if I have P less than or equal to P prime, and P prime less than or equal to P double prime, then I must have it that P is less than or equal to P prime. Alright? That's basically the only condition that I have.
It's transitive?
Yeah, that it's transitive, and there's actually one other condition. If P is less than P prime, and P prime is less than or equal to P, that means that p prime is equal to p. So that way it's like actually less than or equal to, right?
Yeah.
All right. And actually, one more condition. P is less than or equal to P. All right, those are all the conditions on a preorder. And this gives you a category, actually. So for any preorder, which is a set X and this operation less than or equal to, you can create a category. So the objects of the category, they're going to be elements of the set. The arrows are going to be given by the less than or equal to operator. So basically, if x is less than or equal to y, this is equivalent to there being an arrow from x to y.
Between x and y.
Yeah. So composition is because of transitivity. So I have an arrow from x to y, and I have an arrow from y to z. G composed f would then be from x to z, which has to be true because this one, the first arrow f, just means x is less than or equal to y. The second arrow g just means that y is less than or equal to z. By transitivity, that means x is less than or equal to z, which means there's an arrow between them. All right? And then the identity is going to be by the fact that it's reflexive. So x is less than or equal to x. Category theory is boring. Man. I love all the cynical people in the chat. It's great. You fuel me. Alright, so an example.
What is this category called? Is this the category of preorders?
Preorders, yeah. So a good example of a preorder is on sets. So you have sets under the subset.
Oh, yeah.
So you have it that x is a subset of x. So like a subset or equal to, you know?
Okay. Okay, that makes sense.
X is a subset of y. It's a subset of z. Means x is a subset of z. And if x is a subset of y, y is a subset of x, that means y is equal to x. Right? So the subset operation is literally like the thing that inspired preorders. And the other concept that's why it's only a preorder is because you could have two sets that look like this. You can't tell me whether one's a subset of the other because they're not comparable. Right?
Yeah.
And so there's actually a category of all of these subsets, and where there's an arrow between the two if and only if they are a subset of one another. And this is actually used in what is known as the theory of sheaves, this category.
Oh, okay.
So if you know what sheaves are, which you'll probably learn them in algebraic topology. So once you learn what sheaves are, this idea will just confirm. It'll make more sense if you have this idea of preorders in mind, because a sheave is like a functor, really. But when you learn it initially and you don't know category theory, it makes no sense. But if you know it and you know category theory,
I was actually trying to read about sheaves the other day, and like the definition use categories.
Yeah. So sheaves are really. Did you use NLab?
No, that that website's too complicated.
Yeah. Always uses like cyclic terminology. Or like you go on one page and it says use this page for the definition, and then you go on the other page and it links back to the page you came from.
Yeah.
Oh man. All right. And now another example of a category is actually constructing a category from an old category. So you have a category C, you can construct what is known as the opposite category, C-op.
Mm-hmm.
So this category, the objects...
Does that reverse all the arrows?
Yes, it's reversal of the arrows. So the objects are just the objects on C. The arrows is for every arrow F from A to B in C, you can create a new arrow F-op, which is from B to A, which is in C-op. Yep. So it's just reversal of the arrows. All right. I need to turn on my fan. Oh, it's the thing's not even on. Oh, there we go. Whew. Yeah, my arm's getting tense. All right. Now I'm going to introduce what are known as contravariant functors. So it's like a normal functor.
Oh yeah, they're functors from the opposite categories.
Yeah. So.
Or yeah, they flip the composition, right?
Yeah. Yep. So first
Also
thing
learned
for
about that
every...
when reading about sheaves.
Yeah. So you have A, an object of C. There is an object F of A of D. And then for every arrow from A to B in C, there is an arrow F of F, which is from F of B into F of A. So this flips the domain and codomain. I think when I gave the initial definition of a functor, I didn't specify the domain and codomain of the output, but I think you knew what I was talking about. In a normal functor, it would be F of F from F of A into F of B. I should probably make that clearer. And then you have it that F of F composed G is F of G composed F of F. And you have it that F of the identity is the identity on the output. Alright, that's a contravariant functor. It flips the domain and codomain, and it flips composition order. So you could alternatively view this as a normal functor, which is a covariant functor, which is from C-op into D. I hope I did this the right way around. And you do F of an object, A, is just, so let's call this F bar, alright? So for this contravariant functor, you can create a normal functor. So F bar of an object is the object, F bar of the opposite arrow is F of the normal arrow. And I keep forgetting to do stuff. Sorry. So the composition here is F-op composed G-op is going to be in quantity G composed F-op. Does that make sense?
Yep.
Yeah, so you flip the order of composition when doing composition on the opposite category, which allows this to work. Yep, people are still asking math questions. If you're listening to the live stream, you should realize by now that this is not Ask Me Math. Ranuk. What did Ranuk ask? Integration of x to the x from limits 0 to 1. Yeah, I have an old video on that. It's one of my most popular because it's calculus. that's how you make it. All right. Ooh. So you can prove that this is a normal functor. F bar of f op composed g op is equal to f bar of g composed f quantity op, straight from the definition of an opposite arrow composition, which then by the definition of f bar is just f of g composed f, which then f is a contravariant functor, so you flip the order of the composition. So you do f of f first, then you do f of g, which then, by the definition of f bar, is then f bar of f op composed f bar of g op. And then look at that. It's the right way around. It's a normal functor.
Nice.
Yeah. Woo! The live stream's pretty laggy, though. Why is it so laggy? I'm trying my hardest. Okay.
And gay and boring. Nice.
Okay, I'm going to turn down... Okay, can you watch... This would be a bad idea. Discord's what's slowing it down. So it'd be nice if we didn't have Discord slowing it down.
Yeah.
So there's going to be a delay between what you see and what you hear, which is going to be annoying. But
I mean, I could mute
stream...
I could mute you on Discord and then unmute the stream.
Yeah. I think it's working better now. I'm looking at my phone. No. Still looks pretty laggy. Your Patreon link isn't working for me. Great. Just
Yeah, it looks a lot better now.
Okay. Well, we'll just go with this. Alright, I tried, guys. I tried. Okay. Need better internet and better camera. Better camera? My camera's great. Okay, do you guys want to see the crazy setup I have? It's like...
No.
That is insulting. I have professional lighting. I don't care what you think about my quality, because my quality is great objectively, and you're mean. Alright. Can't deal with these haters. Now, I'm going to move on. I wanted to get to universal arrows, which seems stupid now. Alright, how much longer are you willing to bear of this?
10 minutes.
10 minutes. All right. I really want to introduce natural transformations next, but I don't have time. So I'll introduce monics and epics. So a monic is an arrow, which is from A to B, F, and I always forget which order it goes. I have to look in my book. Don't make fun of me. Monic. Epi is right cancelable. Monic is left. Okay. So a monic is going to be if you have two different arrows, G1 and G2, coming into it from a separate C. So F is actually the monic. These are just arbitrary other arrows. And you have it that F composed G1 is equal to F composed G2. Then that implies that G1 is G2. So in a way, it's left cancelable. This should remind you of the definition of a surjective function. F of x, or an injective function. F of x equals f of y means x is equal to y. If they have the same input, they have the same output. Let me make sure. I need to make sure I'm getting this right. Because if I teach you something wrong, that's injective. Yeah, that's. I corrected myself. I don't know if you heard it.
I didn't.
Yeah, sorry.
It's all good though. That's good.
Yeah, no, it's the right way around. An epic is like a surjective function. So you have an arrow f from A to B, and then you have two arrows going out of it, like this, into C. If you have it that G1, ooh, that's running out, composed F is equal to G2, composed F, that means G1 is G2. So that is surjective. I can't keep messing this up. So the reason why it is surjective is because the range of f would need to be the entire space for these two functions to be guaranteed equal by that. Alright. Now there's also the idea of an initial object, which is an element of the object of a category, and you have it that for every B, an object of the category, there exists a unique arrow, which is F from A to B. So that means that there is only one arrow from A to B, and it's this unique one. And that is for every single object. This is, say this is the initial object. This is every other object of the category. It would look like this. Like that. Alright?
Yeah, so what are the conditions for this happening?
So every single object in the category, there's one arrow, one unique arrow, from the initial object to the arbitrary object. Unique arrow.
So is this something we're constructing or defining, or?
This is a definition. So this is what an initial object is.
Oh, okay,
so
okay.
If you have something, so an example of initial object is the 1-point set. So just any 1-point set. This is an object of the category of sets. Alright? there is only one function from the one, sorry, I messed that up. Empty set. Empty set is the initial object. Sorry, so the empty set, there's only one function from that set into any other set. And it is the function it's the trivial function that sends nothing to nothing, right? There's no
Wow.
elements here. It doesn't need to do anything. And that's a unique function between them. Alright, does that make sense?
Yeah.
In the category of groups, the zero object, the trivial group, is an initial object. It'll send the identity to the identity in the group. And that's the only object of the trivial group. And that is the only morphism between them. And that's for any group. Yep. Alright, then there's the dual idea of this, which is a terminal object.
And that's everything has an arrow to it.
That is, yeah, everything has an arrow to it. So for every B, an element of the objects of C, so this is an A. Usually you'll see T, actually. There exists a unique arrow F, which is from B into the terminal object. So this is the terminal object, these are the other objects. All the arrows are going into it. Alright, can you think of an example that I kind of spoiled for this?
No.
Specifically in the category of sets. So we're in the category of... what are you gonna guess?
Like mapping, like just a constant map? I don't know.
It's not a map, it's an object.
Okay. So an object.
What is the object? What do you think it is? I'll tell you.
The set of all sets.
Nope, that is wrong, and that is actually not a set at all.
Shut
That's
up.
Russell's paradox. Alright, so the actual terminal object is the 1-point set. So any set with just 1 point in it, that is a terminal object. So there is only one function from every other set into the 1-point set. And it's the one that sends every element to the single element. You cannot construct a different map. And for every single function, this map exists. So that is a terminal object.
Okay.
So what you should also note is that something like the 2 element set is not a terminal object. Because even though for every single set X, you can construct a map, say sending it to the element A of the set, but it's not unique because you can construct a different map into the same set, which would just send it into the second element. Because there's 2 different maps, it's not a terminal object. But the 1 element set is a terminal object.
Okay.
Alright, and there's another, in the category of groups again, the trivial group is a terminal object as well. Because between any group and the terminal object, there's one single map. Sends every element G of the group to the identity element. Really easy.
Yeah.
Alright. So what you should note is that the trivial group is both a terminal and an initial object. And this is the reason why we write it as a 0, is because it's literally a zero object.
Okay.
So a zero object is one that is terminal and initial. Alright, so the zero object on groups is a zero object. The zero object on a trivial ring is a zero object. Stuff like that. Alright. So if you have a zero object, that means that for any two elements, A and B, of the objects, and you have a zero object 0, then by the definition there is a unique map which goes into the zero object from A because it is terminal, and there's also a unique object that goes out of the map into B because it is initial. And because we're in a category, you can compose these two and create a unique morphism 0 from A to B, which goes through the zero morphism. And in fact, because this is because of the uniqueness properties, you can actually prove that this has a two-sided inverse, or that it goes both directions. So 0, B to A.
From B to A, yeah.
Yeah, from B to A. And that these two are inverses, so that when you compose them, get the identity. I'm trying to think which order I did this in. A. And then when you compose them the other way around, you get the identity on B. And so what this means is that if a category has a zero object, that every single object of that category has a canonical isomorphism between them.
Okay.
Yeah. I think. I hope. If I did that wrong, that'd be dumb.
So that's a pretty strong like condition. So the category of groups has that because the trivial group is a zero.
Group.
Okay.
Wait a minute. I might have done that wrong. They might not be inverses. No, they have to be inverses because they're unique. I don't know. Wait, let me think about this. Okay, because those maps are unique, they're inverses of each other. So if this is F and this is G, this would be G inverse and this would be F inverse. Yeah. Yeah, so I was right. It might not be two-sided, though. I might be wrong on that. Yeah, because this is at least I said that weird. They're at least one-sided inverse, because there is a unique map from the zero object to itself, which is just the identity, and because of composition, you'd have it that, okay, let's call this one L and this one K, just to avoid confusion. If I did F composed K, this is from 0 to 0. Because 0 is a zero object, that means that it's unique, which means that it's the identity. So that's a one-sided inverse. The it being a different directional inverse is not true. So there's not a unique isomorphism between them. It's just It's close to. Yeah, that was too good to be true. And same thing with L composed G. So those are both just one-sided inverses. So L composed K. Is it L composed K or is it K composed L? It's K composed L. K composed L. Composed G composed F. Would in fact, so it is a one-sided inverse. So, yeah, because this one right here, by associativity, is K composed L composed G composed F. Oh, no, it's not even a one-sided inverse. Yeah. So no, they're not they're not special. It's just the zeromorphisms are heavily related. Alright. Sorry for that misinformation. I'm doing this without notes. Alright, I think that's it for me. Want to take a
Okay,
little
wait,
break?
can you explain one thing?
Yeah.
So I read in the McLean book that the one object category is like not the category 1, but just like the one object category, that it was like basically a monoid, and like it depended on the arrows.
Yeah. Let me.
So
Okay. Yeah, it's really cool. Let me show you. All right.
because
So
I didn't
for-
understand how you could have multiple arrows like
on a single object
that don't qualify. Yeah.
as the identity.
Yeah, but like how they're not all like how they aren't all the same arrow.
Yeah. Let me.
Like it didn't make sense.
So you can have multiple functions between a set in itself, right?
Yeah.
So that's basically what it is. I'm going to explain it in a way that I really like. So if you're given a monoid M, and it has an operation dot, you can construct a one-object category. Alright? And the way you do it, the object is going to be the set M. The arrows are going to be phi on elements of the monoid. So for every M an element of the monoid, you can construct a map phi M, which is from the monoid to itself, because there's only one object. This is so like that. Just the monoid is the one object. And then the arrows are going to be these types of maps, which will send an element A to M times A. So for every single element M, you construct this map, which is a automorphism on the monoid, right?
Mm-hmm.
And so that's many different arrows on the same object M for every single element M. So for every element of the set, of the monoid set, you can construct a map from itself to itself. And that right there is a category on one object. And then the composition is composition of arrows.
Okay.
Of functions, I mean. And then, what you could also do is go the other way around, where if you have a category on a single object, so you have a category on a single object, let's call the object A, let's have arrows F, G, and H, you can construct a monoid.
Mm-hmm.
Alright, so the monoid will be the set of arrows on the category, and then the operation between them is composition. So that's the multiplication. It's composition. that would create a monoid under those operations.
Yeah, that makes sense. Like the automorphism thing makes a lot of sense.
Yeah, I can't pin things, I don't think. Yeah, I can't pin things. Alright. So I think we're doing alright. So
I think
we'll
we should
go
take a
to...
break.
Yeah.
Just yeah, just a few minutes. I'm
Yep.
hungry.
Alright.
Now you can fulfill your Ask Me Math followers.
Oh
For
man,
like
no, I need to get
5.
water.
Yeah.
Woo! Yeah. All right. Ask me
So
math for 5 minutes.
you should also set up so that your live stream records my camera whenever I'm ready.
Yeah, I already have it set up. Yeah. Integral of random thing. I don't like inverse. I don't like integrals. I like inverses, just not integrals. How many viewers do we got?
12, 13.
That's pretty epic, not gonna lie. Alright. We're gonna go a little overtime, guys. Because we also started a little late. Alright. Think we're good. So, enable preview. Okay. Guess what, guys? I'm going to do what's called a pro gamer move. I'm going to absolutely do nothing of importance except just change where my camera is facing. So, watch out, guys. Okay. How am I? There. Oh yeah, look at that hair. Alright, I need to prop this up a little bit. There we go.
Play us a song on the guitar.
I don't own a guitar.
Yeah, you do.
How
It's
do
in
you
your room.
know? Oh, it's a ukulele.
Whatever.
It's just a small guitar.
Mm-hmm.
Wait. That's the Harambe song. That's the only song I know. Hopefully you guys won't see my mic when I do this. Ugh. I don't think you can sort. There we go. All right. And then guess what, guys? It's not in frame, but it's very bright. There we go. Hey, look at that. Whew. The camera's like way over there. Turn off autofocus. There we go. Yeah, it's gonna be weird for you guys to see this. I have to be all the way over here. Wait. That probably is a little better. Hello, it is I am gonna be changing the crop settings on myself in stream.
Okay,
Oh yeah, there we go.
I'm slightly more ready now.
Sloop, there we go. Oh, look at this epic setup. Oh my god. Wait. Beautiful. Now it looks natural. I'm gonna turn off all my lights actually. Just pure natural light. Looks much worse. But it gets hot, so it probably makes more sense for me to be here. Alright. Okay, I am on streamer mode. Sorry, I love my dad, you just sent me something. Alright. Turn on your webcam whenever you're ready, buddy.
Alrighty.
Oh yeah.
Oh boy.
Let me see how good this looks.
It's like slightly out of frame. So, whatever.
Monica looking like a cutie right now, not gonna lie. Yep, okay, it looks pretty good.
Nice.
Yeah, and my
Well, I guess
this is it.
Hold on, let me put my my frame magnets. Shit.
Okay, it's going very slowly for me, but the stream quality is pretty good.
Alright. Well, we'll make do.
Yeah, it The stream was probably
Okay.
like that for like most of it.
Oh no. I hope my purple marker isn't dying. I don't think it is.
Projective Geometry.
Yes. So that's what I'm gonna be teaching today. Projective geometry. So we first start with definition of signed distance.
Sine distance. Ooh.
In particular, we're using a signed ratio. So XA over XB. And this can take on two possible values. One is negative. That negative is really thin.
The lengths
Okay,
of the
I'm
two
gonna have to
lines.
make this bigger. If essentially you have this configuration, so A and B, and X is in the middle, not necessarily the midpoint, but just in between A and B, then
collinear.
yeah, well, it has to be collinear, but it's just that it's negative if it's in between, and positive if X is outside of the segment AB. So if it looks like this, then XA over XB is a positive number.
So that's just given three collinear points. You can do the signed ratio.
Yes.
All right.
Now, if we have a line and we have 4 points, and I'm going to pair them.
Hey, Steve. What? Oh, Steve's the black button red pen. I was confused. Ooh,
Yeah.
4 points. That's getting out of
Then
hand.
they don't have to be ordered like this, but I'm ordering this because this is the most common way to do it. Then we write the cross ratio. So this is called the cross ratio. ABXY. And this is a semicolon. And this is defined as XA over XB times YB over YA.
And that's the signed distance.
Yeah, so these are both signed fractions. So when it's like this, so X is between A and B, so this is negative, and Y is outside of A and B, so this is positive. This is the most typical this is the most typical orientation of the points that we're going to see in projective problems. So in particular, if A, B, and XY intersect, then they have a negative cross ratio. But if they're disjoint, so like AX, is that too light? Yeah, that's way too light. I think this marker's dying.
Sad.
So like AXBY, this would be a positive cross ratio because AX and BY are disjoint from each other. So this would be greater than 0.
So, okay, so the value of that one would be, yeah, okay, I think I get it. Because both of the things in the product would be negative, and then they multiply, and you get something positive.
Let's see, BA or BX. This in particular, this would be, both would be positive, I think.
Yeah. Yeah, you're right.
And if if it's contained, so you have like xb ay. So xb is inside of ay. This is also positive. I think both of these would be let's see, ax, ab, yx, yb. Yeah, so these are both positive ratios. But this ax by, this gives you a negative value. And we're going to see later that negative values are the most common.
All right.
In particular, -1 is going to be the most common, but we'll see why in a bit.
All right.
So that's the cross ratio of 4 points. Now we'll have the cross ratio of 4 lines. So if we have a point P and 4 lines that all cross at P, I'm going to call this line A, this line X, this line B, and this line Y. So these are the names of the lines. Then we can define the cross ratio of AB XY in terms of the angles that these lines make.
All right.
So the angle between X and A, these are lowercase, X and A, I might not, let's see, sine. Okay, I barely had room for that. So it's like the same lettering, but instead of distances, we're doing the sines of these angles.
So are these concepts related on like a higher level than just like
what do
a
you mean by that?
formula? So could you, I don't know, but I'm just saying, like, could you get one
Okay,
of
so
the
what
formulas from the other?
Yeah, so it's like before we had, you know, the distance XA was here. So it's like it's the same lettering as before. But what this allows us to do is if we have 2 lines, that's making white. If we have 2 lines, let's say here and here, and we have these points as these 4 points as intersections and these 4 points as intersections, then the cross ratio of these 4 points and the cross ratio of these 4 points are equal. And I'm going to prove that. So
are they related to the cross ratio of the lines?
Yes.
So they're both equal to the cross ratio of the line?
Yes, so that's the theorem here. I really hate that this marker's dying.
Oh, 1.1.
So
I
if
didn't
we
really
have...
organize mine that well. I'm sorry.
That's fine. I mean, I'm going off of like pre-printed notes, so...
Yeah.
I mean, I guess you had a textbook, but you were also like not looking at the textbook. I'm also like just looking at my notes. So AX, B, Y are points on a line. And P is a point not on that line. Then the cross ratio AB XY equals the cross ratio PA PB PX PY. So here these are lines, these are the 4 lines that you have, and these are the 4 points.
Yeah, that was the question I was asking before, whether you could do something like that.
Yeah. So, let me go to where I have the proof of this. So to prove this, we have to use the law of sines. So let's say we have, this is really fading. Okay, so let's say we have something like that. And again, I'm gonna use the ABXY because that's what I have on my paper. I don't want to confuse myself. So if we take a look, so this is the point P. Oh my gosh. I don't know what my marker's doing. All right, that's the point P. And if we look at the triangle PAX, then we see that
I should be taking notes. Wait.
So the law of sines tells us that AX divided by the sine of the angle XPA is equal to PX divided by the sine of the angle PAX.
Yeah.
So that's the law of sines. So this allows us to basically rewrite AX. I'm gonna need a lot more board space. All right, I'm just gonna erase the theorem here.
All right.
But it's saying that the cross ratio of the 4 points is equal to the cross ratio of the 4 lines. So here, so now we have AX. I might have to switch markers.
So is it common to use parentheses or brackets, or like arrow brackets?
Parentheses. I've only seen parentheses.
All right.
That blue is bad. Oh boy. I really just want to use my red marker, but we saw yesterday that that wasn't very bright.
Yeah, that works.
I think
pretty
that's
well.
good.
Yeah.
Yeah.
As long as
All
it's
right,
not
I'm gonna
dead.
use red now. Yeah, it's not. Okay. So we have AX. It's also much easier to write with this one.
Small, yeah.
We can rewrite it. I like to write it like this. And in particular, we have, let's see, where is it? Yes. So we have equalities just like this. So for BX, if you looked at triangle PBX, you could do the same law of sines thing. And you'd get a much similar result. Now, what we want to notice here is that PAX, so this angle, is equal to PAY because it's the same angle, we're just extending this point over here. And PBX, which is this angle, is the same as PBY. And that will help us later. So we also have, let's see, I should be writing this the way the cross ratio does. So this is XB and this is XA. Doesn't make too much of a difference, but now if I write YB, and I'm gonna write it backwards because the cross ratio is backwards. YB is equal to py. So we're doing the law of sines in the triangle PBY.
PBY. All right.
So YB is equal to PY times the sine of angle YPB over the sine of angle PBY. And YA is equal to PY, the sine of YPA over the sine of angle PAY.
All right.
So now, so we have our expression for ABXY, and we said that was XA over XB times YB over YA.
Yep.
Now all we have to do is plug all of these four equations into this one.
All right.
Yeah. So I'm just gonna get rid of that stuff. So XA is PX sine X. I'm just gonna drop the angle notation. But
Yep.
over
So we're gonna have to
and
do
then
this into the piecewise function, right?
yeah, so in a more general proof, you would go through all the different cases, but I'm not going to do that. I'm just going to show the proof for this case. They're all pretty much the same. It's just law of sines in any order.
Yeah.
YPB.
That's clever.
Okay. So now, like I said earlier, angle PAX is equal to angle PAY because we're just extending through this ray.
Yeah.
So these two signs cancel out. And similarly, PBY and PBX are the same, so those two signs cancel out. PY and PY cancel, PX and PX cancel. So what we get is sine XPA over sine XPB times sine of YPB over sine YPA. And this is the definition of the cross ratio of the four lines PA, PB, PX, and PY.
Yeah.
So we've now shown that the cross ratio of the 4 points is equal to the cross ratio of the 4 lines.
Yeah.
So, like I said earlier, that allows us to, if we draw another line and put points here, 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 and here, then we can say, okay, the cross ratio of these 4 points is equal to the cross ratio of the lines, which is equal to the cross ratio of these 4 points. So this is what we would call a projection through P. So we take these 4 points and we project them onto another line.
So the reason the cross ratio is the same is because it's a similar. It's just like contracting it down.
Yeah, yeah. So it's an invariant under projection.
Yeah.
This would be a very mathematical way to say it.
Yeah.
So there's that. Oh, Oh boy, now I have to draw circles.
Woo!
Woo! So now we talk about cyclic quadrilaterals, which are very important in particularly competition geometry.
Quadrilaterals that blah 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 that are on circles where all the vertices.
So all 4 vertices are on a circle.
You just drew like a square.
Shut up. Yeah, it's hard drawing cyclic quadrilaterals that look unique. Let's see. So if we have, okay, so let's say we have our circle. I don't think that's too bad. Let's see, we have a point P, and then
should I start a new page for the notes? Because this is gonna take a lot.
Oh, what do you mean, like a new?
Like a new
page
in my notebook.
Just for this?
Yeah.
I mean, it depends how much space you have. It shouldn't take too much more than the other one.
Yeah, alright. It took a page for the other one.
Okay. So we have this quadrilateral, and we define, or not define, but we say that no matter where this P is, so P is just a point on this circle, and we claim that the value of PA, PB, PX, PY does not change when you move P. And it is equal to plus or minus the same cross ratio looking thing we had before. But now these aren't the sign distances, because these aren't linear or collinear points. The plus or minus takes into account the configuration of the 4 points. So plus is this diagram corresponds to a plus because A, B, X, Y, it's in that order on the circle. But if it were flipped, if this were an X and this were a B, then it would be a negative.
Yeah. In
other words, if AB and XY intersect inside the circle, it's negative, but if they intersect outside of the circle, it's positive.
Ah, yeah.
So that's the plus or minus convention. So now we want to prove that this is true. So again, we use the law of sines to rewrite our XA and XB. This time, however, okay, so what line do I need to draw? I need to draw from X to A. Okay, so if we look at the triangle ABX, something like, I'll draw it a bit bigger. Oh my god, I hate drawing. Yeah. I'm sure the comment section is telling me how bad I draw.
No, they're tangentially related.
Yeah. So in this triangle, we have, again, the same relationship as before. So XA is going to be sine, except I'm going to write it differently. Is the sine of XPA, because that's the angle XPA PA. Hold on. Sorry, I think I'm looking at the wrong triangle. We are looking at
ABX.
XPA.
XPA. That would
So,
change it.
okay,
Yeah, that would make
that's the right triangle. So XA is equal to sine of XPA times PX over sine of PAX.
Why are you writing it that way?
I am writing it that way because I'm gonna also look at triangle PBX, so like something like that, PBX, and we can write XB is sine XPB times PX over sine PBX. But here's where the cyclic quadrilateral part comes in. Because PAX, which is this angle here, and PBX, which is this angle here, they both are inscribed on the line PX.
Yeah.
And when you have two angles on a circle that have the same, that are
I see where this is going.
they're scribing the same chord, PX, then these angles are equal. And if B and X were swapped, then they would be supplementary, I think, or maybe they're still equal. Either way, like I'm just showing the proof for this configuration.
Yeah,
so in particular,
plus.
we'll have the plus here.
Yeah.
But you can go through the details for the other direction and get the negative. So these two angles are equal because of the cyclic quadrilateral condition. So when we divide XA by XB, we just get sine of XPA over sine of XPB.
Yep.
Similarly, YB over YA would just be sine of YPB over sine of YPA. And when we multiply these two together, we'll get the sine ratio, which is equal to this, the cross ratio of the four lines. Because XPA is the angle between the line PX and the line PA.
Yep.
And in particular, since we now can write this cross ratio of a cyclic quadrilateral in terms of the lines, then we also know that this is equal to, we can project onto a line. So let's, I'll draw a new picture for that.
That's gonna be huge, isn't it?
Yeah. Let's see. We could just. It's fine. So if we project over here, and we project over here, and then extend this line, or something, I don't know. We have these 2 points, A prime, Y prime, and I just say they'll stay on the same line, but you can make a whole new line, it doesn't matter. The point is we can now take these 4 points that are on a circle and relate them to 4 points that are on a line, and they have the same cross ratio.
All right.
So that makes sense, right? Yeah.
Yeah.
Okay. Now we talk about why I said the negative was so important.
All right.
We now talk about harmonic bundles.
Okay, wait. Before we go into that,
Sure.
does that necessarily prove that it's invariant under change of P? Oh, is it because the projection would always have the same line? Like cross ratio?
What do you mean? The change of P? Because one expression didn't have P in it. It just had A, B, X, and Y.
Oh. Oh, yeah,
Yeah.
it did. I'm dumb, yeah.
Yeah. So since it doesn't have P in it, it doesn't change when P changes.
Yep. Thank you.
Okay. So, harmonic bundles are points, say A. So again, I'll do the weird configuration where we have AX, BY, but we still write the cross ratio AB, XY. You might ask, why is that? A harmonic bundle is simply when the cross ratio is -1.
Why is that called a bundle?
I don't know. It's not my choice of words. In particular, if we have that these are negative or -1, then AB YX would also be -1, and XY AB is also -1. So it doesn't matter the order of the points anymore. What matters is that A is paired with B and X is paired with Y. That's all that matters when we have a harmonic bundle.
Yep.
And then another thing, so I guess this isn't really related to harmonic bundles, but another thing that we have in projective geometry is the so-called point at infinity.
Yeah. Oh yeah, I was wondering when this was coming in.
Yeah. So this is going to be since these are like competition notes, so it's not going to be as rigorous as you might see in like a projective geometry book, but essentially let's say we have two lines. If when we're dealing with geometry problems and we say like we want to know if two lines intersect and where they intersect, and we want to do stuff with those intersection points. But if we have a theorem that relies on the intersection point, what happens to the theorem when the two lines are parallel? We don't want the theorem to break. So what we say is that they intersect at a point at infinity, which I will just write as infinity. And there are multiple points at infinity. You can think of it as a equivalence class, so that lines that are parallel have the same point at infinity, and lines that are not parallel do not. So every line has a point at infinity, and parallel lines have the same point at infinity.
Yeah.
So we say that these lines intersect at infinity.
Very cool.
So now, what do these two things have to do with each other? Well, let's say we start with a good old line segment, AB, and we have its midpoint. So using the assigned distance, MA over MB, this is negative, but we know that MA and MB have the same value, just opposite signs. So this is equal to -1.
All right.
But now, if we extend this line off to infinity, we have infinity is at an equal distance from A and B. It's an infinite distance, but it's the same distance. So infinity A over infinity B, or actually I'll write it this way, infinity B over infinity A, is equal to 1. So if we multiply these two, we get AB, the cross ratio of AB, M, and infinity is equal to -1. So this is a harmonic bundle. And it's a very important harmonic bundle because a lot of geometry problems deal with midpoints. So now we have a condition for what it means to have a midpoint. Essentially, in projective geometry, we want to get rid of the intuition of distance. There is no distance, so this is a way for us to manage that. So we can't say these two have the same distance. We just say that there's a harmonic bundle here. And in particular, we'll see, I hope I get time to later, where we can project essentially a midpoint into other points, and we get cool relations with that. So now we're going to call this lemma 1. So just for future reference, lemma 1 is that AB and the midpoint of AB and the infinite point on the line AB, those form a harmonic bundle.
Why did you start with theorem 1.1 and then you moved on to lemma 1?
Because we're in a different section now.
Alright, so is it lemma 2.1?
Sure. It just writes, the notes write it as lemma 1, so, you know. Okay, so now we have, if we have a triangle, A, B, C, or draw it like that.
The ice cream truck's here.
Dude, go get some ice cream. Shoot, hold on. Okay, I'm gonna move this to the right more because I think I'm gonna need space. Dude, I hear it, dude.
Yeah, it's very loud. Oh, don't tell me it's gonna stop right outside my... Oh god, it moves so slowly. I feel bad because it's just... It's really nice. But, like, I don't want ice cream.
Okay, so we have this configuration. This is D, E, F. And then we have this line going like that. This line going like that. Okay, they intersect there.
So are F, E, and D midpoints?
No, so call this point P. These are just arbitrary, what we call Chevians, I don't know.
Yeah.
They're
What's it called?
I'll just say Chevians. I think that's wrong.
Intersect.
Yeah, so it's just 3 lines that intersect. They could be medians. They don't have to be medians.
What's it called?
This, Chevians. I just drew
the
a
3
line
lines. There's a different name for it.
That's what they're called.
Really? That's not what I learned. I learned a different word.
Oh. Okay.
So it confused me. Alright.
Okay, so... Yes. So AD, BE, and CF all meet at a point P. And line EF meets the line BC at point T. Then we claim, this is lemma 2, TDBC is a harmonic bundle. To prove this, we just use 2 very common theorems in geometry, namely the theorems of I think it's Cheva, but that sounds weird, and Menelaus, which essentially deal with configurations like this. So Cheva is used for when you have the triangle and the points, or the lines that all intersect at a point. What it says in terms of our directed distances, or assigned distances, is that FA divided by FB times DB divided by DC times EC divided by EA is -1. So typically you'll see it as a 1, but since we're using signed distances, these are all negative. These ratios are negative ratios, since all of them are in between A and, like, F is between A and B, so this is negative,
Yeah.
this is negative, this is negative. So they multiply to -1. Menelaus deals with when you have a triangle and a line going through it, like that. And it says that FA over FB, which is negative, times TB over TC, which is positive in this case because T is outside of BC, and EC over EA is also negative. So negative, positive, negative. It says this is equal to 1. So that means that if we divide these two equations, these cancel out and these cancel out, and we would get TB over TC times DC over DB is equal to -1. And I wrote it differently, but this is essentially TD BC. Since the order of the points doesn't matter in a harmonic bundle. What matters is that T and D are paired and B and C are paired. So this proves that TDBC is a harmonic bundle.
All right.
I believe I have proofs of both of these theorems. So you can look that up.
All right.
How are we doing on time? It's 3:16. Okay. Going a lot slower than I thought. Well, I guess I'll get to lemma 4, and I will probably stop there. But
yeah,
which is kind of sad. I didn't get to talk about a lot of stuff. But so now, since we have harmonic bundles, which are points on a line, we now talk about harmonic quadrilaterals, which are cyclic quadrilaterals, which have a cross ratio of -1. So let's say we have our circle. Hey, my circles aren't too bad today. I need more curvature here. That's better, kind of. Okay. And so we have AXBY. So again, the order here makes the cross ratio negative. Write it like that. I need to be pretty precise here. I hope this works. Okay. So that's B and that's Y. So so these are a cyclic quadrilateral, and goes like that. Furthermore, we have the tangents at X and Y. Oh, it didn't work. Okay, I'm gonna move B slightly. Okay, so the tangents at X and Y meet at a point P, and P lies on the line AB. So these 3 points are collinear. That's why I had to move B, so that would work. So ax by is cyclic, and the tangents at x and y meet at P, which is on AB. So this is the whole if. So we construct it this way. Then we claim then AX BY is harmonic.
Yeah.
So AB XY is -1. That's what we want to prove. And this is our lemma 3, the first part of it.
And so the same thing happens with the last one where you project it onto a line to define the cross thing, right?
Yeah.
Yeah. All right.
Well, we just say that this is the same as, you know, XA divided by XB, but we take it to be negative because here AB and XY would intersect in the circle. Yeah. So we just take it to be negative.
Oh, okay. Yeah. All right.
Yeah. So since, let's see, so P BX, so this, I'm gonna move my label here. So that, this is all one line. PXA, so PBX, PXA.
PXA.
Okay, so when we have a tangent to a circle, so let's say that. So let's say we have 2 points here, x, xb. So I'm just drawing something here. Okay, so this is tangent P. When we have a situation like this, so that PX is tangent to the circle, in other words, if this were the center, then this is perpendicular. Then PXB is the same as any angle that inscribes BX.
So it's the same as the arc between B and X.
So these,
so
these two
half.
angles, yeah. So these two angles are congruent if PX is a tangent. So that means these angles are congruent. And this angle is congruent to itself, obviously, because congruency is reflexive. Reflexive. So P, the triangle, where is it? The triangle PBX is similar to the triangle PXA.
Oh, yeah.
That tells us that, so if I draw, let's draw these slightly to scale.
Yeah.
This is B, this is P, this is X, and this is, so pretend that these are similar triangles. PXA. So this tells us that XA over XB, which is the ratio between these two triangles, because these are corresponding sides, that's equal to PX over BP. PX over BP. Now, we also have, when we have a point and it's got two tangents to a circle, we know that the tangents are equal to each other. That's a common geometry theorem, that two tangents are equal to each other. So px is equal to py. So this is equal to py over pb. So similar to this statement, we also have that triangles PBY is similar to triangle PYA. And so I can draw that just by replacing an x with a y. These are very bad similar triangles, but so like that. So PY over PB is the ratio between these two triangles, and that's equal to YA over YB.
Yep.
So we now prove that these two ratios are equal, and that means that AB XY, which is, we know it's negative, we know it's the negative of XA over XB times YB over YA, and we just proved that these are inverses of each other, so this is equal to -1. So that means that this AXBY is a harmonic quadrilateral.
Yep. Woo.
So that, yeah, and that's part one of the lemma.
Oh my god.
Now, don't worry, part two is much easier once you have that.
I only have one page left. Oh, this is scary.
Part two. So if these diagonals intersect at a point Q, then AB PQ is a harmonic bundle.
All right,
the way
I'm not
we
gonna
get
write the proof down for this one.
Okay, it's really nice though.
Oh.
So we already know AB XY. So this is equal to -1. So what we do is we actually use projection.
Oh my god, yeah, that is nice.
So if we look at the point Y, so we're gonna project AXBY onto this line AP. So A and or I guess I should call it the line AB. So A and B are already on the line, so those don't change. And when we do a projection, we write the point that we're projecting through over the equal sign.
Yeah.
So I don't know if I condensed this, but essentially, so we're taking these points on the circle to these points on the line. X, because XQY is one line, so XY, X gets projected to Q. And then where does Y get projected? Well, this is the weird part because we're asking where does Y project Y to? And the way we do this is with the tangent, because the line YY, we just define it as the tangent, and this will only ever come up when you have a point on a circle. So we just define it to be the tangent. And where does the tangent to Y intersect this line? Well, it intersects at P.
Yeah.
So by projecting through Y, we get that since this is harmonic, this quadrilateral is harmonic, then these 4 points are also harmonic.
So I don't know if you can fix this, but your mic's maxing out a little bit. So you should maybe move your mic a little further from your mouth when you're talking.
Okay. Okay. Alright, so yeah, that's lemma 3. So we have 2 harmonic bundles in this configuration.
Right. Lemma 4! This is it!
Lemma 4! This is it. So...
a half hour over time!
Woo! Okay, so we got that triangle. A little something like that. And a little something like that. So this is A and this is Y.
Is that point at the top of C?
C, yes, sorry. Lemma 4 says that if we have this configuration, X, A, Y, B are collinear in that order, and C is a point not on the line, then any 2 conditions, any 2 of the following conditions imply the third. So the first condition is that angle XCY, which is this angle here, is equal to 90 degrees, so it's a right angle. Condition 2 is CY, so this line bisects the angle ACB. So that's this angle here. And the third condition is AB XY is a harmonic bundle. So the lemma says any 2 conditions imply the third.
Mm-hmm.
Third. Okay, so what we want to do is rewrite these conditions so that the statement of the lemma is more obvious. How we do that is by projection. So we take CX and we construct a line parallel to CX, but passing through Y. So a little something like that, and a little something like that.
Make the diagram bigger.
So in particular, under this projection, X would be mapped to the point at infinity, because these 2 lines are parallel. So let's look at condition 1. If XCY is a right angle, then since these lines are parallel, that means this is also a right angle. So this condition is equivalent to saying angle CYA prime. So A prime and B prime are these new points. That's where A and B get projected to. Or another way of saying this is that CY is perpendicular to A prime, B prime. Or we could also say CY is an altitude of C, A prime, B prime. So that's condition 1. This is all the things that it's equivalent to. Condition 2, so we have this angle bisector. Well, the angle ACB is equal to the angle A prime CB prime, because we're just going along the line. It's still the same angle. So that means that if CY is bisecting this angle ACB, it's also bisecting the angle A prime CB prime, which means that CY is an angle bisector of C A prime B prime. And condition 3, if ABXY is -1, then we know that cross ratio is invariant under projection. So under our new projection at C, A and B get mapped to A prime and B prime. X, as we saw, got mapped to the point at infinity, and Y stays the same by definition, because we define this line to be passing through Y.
All right.
So what that means is that this is a harmonic bundle. But we saw before...
Bye, black pen, red pen. Say bye, black pen, red pen. I love you, black pen, red pen. That's what someone said in the chat. C-Day Anamu Games is helping people out in the chat as well. Woo! Man, Lemma 4.
Lemma 4. Okay, so, and we saw before by Lemma, I want to say it's Lemma 1, that if we have a segment and its midpoint,
Yep.
so A, M, B, then AB, M infinity was -1. So if A prime, B prime, infinity Y is a harmonic bundle, that means that Y is the midpoint.
So that is the only harmonic bundle with infinity?
With infinity, yeah.
Alright.
So this means that CY, so if Y is the midpoint of A prime, B prime, then CY is the median of a CA prime, B prime. So in particular, all of these three conditions that we had, we can rewrite in terms of CY being some piece of the triangle.
Oh.
And the lemma says if any two conditions imply the third. And that's true because if we have this triangle, A prime, B prime, and C, so we have CY here. If we say it's both an altitude and an angle bisector, then that means it must be a median, because that's going to imply that this is an isosceles triangle. And it's essentially saying that that the coincidence of this of like being an altitude and a median, or an altitude and angle bisector, or a median and an angle bisector, these all imply that this triangle is isosceles, and therefore it implies the third.
Yep, that's very cool.
Yeah. So that is lemma 4.
It's lemma 4.
Oh.
30 minutes over time, but we're good.
Yeah. I wish I would have gotten to do more, but it's fine.
What did you want to do?
Oh, there's like, what, 10 pages of notes left out of 4 or 5? Yeah, the 5 that I went through. So yeah, there was a lot more.
10 left?
Yeah, so after that there's no more lemmas. There's a problem. I mean, I can do this all on my own page, but there's problems and then more theorems, and
wow.
So we didn't even touch the cool stuff, but this is the
basics.
we
didn't touch the cool stuff in category theory either. Yeah, I guess it just takes a while to teach stuff.
It does indeed.
Wow.
Right, where did I put the other page? So yeah, that's That's projective
All right,
geometry.
we're gonna have to do this another time, I think, so that we actually get to the cool stuff.
Yep.
That was pretty cool though. The projection stuff, I never thought of using projections to prove.
Yeah.
Yeah. That's
Yeah.
a
If we made it
technique.
if we made it past the next example, then we would have gotten to do inversions as well.
Circle inversions?
Yes, because it turns
Those
out
are
they're
so
closely.
cool.
Yeah, it turns out they're closely related. So.
Oh man. Yeah, I saw that number file video on circle inversions.
Mm-hmm.
Have you seen it?
Yeah. That was so cool.
Yeah, it's really nice. Yeah. Oh wow. Yeah, we got okay. Yeah, we gotta do that some other time. Monica, will you cover homotopy type theory maybe in future videos? Homotopy type theory. Homotopy theory, yeah. Homotopy type theory. I'm not exactly sure the distinction between those two things. So I'm gonna sloop. Oh, the thing was in the way very slightly, but you guys couldn't see it was cropped. Alright. He gave me the answer to the integral that he asked me about.
Yeah, now we should do like just ask me math because I don't feel satisfied. We can just keep going.
Yeah.
I don't feel like teaching more. I don't feel like anyone wants to learn anymore.
Yeah, I think this is just transitioning into an Ask Me Math, which I always just like randomly transition between them, which I'm no longer going to do. I'm actually going to end this live stream and then start another one for Ask Me Math. Guess what, guys? I'm evolving as a character. Alright. That's it.